All right, Faraday's law. Faraday's law is a major topic in physics, and before going into it, I'm going to look at two things first. The first is magnetic flux, and the other is induced EMF. So flux measures how much field passes through a cross-sectional area. So for magnetic flux, it's going to measure how much magnetic field is passing through a given 2D cross-sectional area. The quantity of magnetic flux is based on three things: the field strength, how big the area is, and then the angle between those two vectors. It's represented by the Greek letter phi, and it's defined as the scalar product or dot product of two vectors. One is the magnetic field vector, and the other one is something you don't normally think of as a vector, but area. So an area vector is a vector that directs perpendicularly outwards from a 2D surface. And dot product can be written as the product of the magnitudes, so the number assigned to both the field and the area, times cosine of the angle between them. And then oftentimes it's just written as phi equals BA cosine theta. Now the smaller the angle is, or the more parallel the field vector is to the area vector, the more flux you're going to get. The bigger the angle is, closer to 90 degrees, there's less flux. And then when they're perpendicular, or when theta is 90 degrees, there's no flux through the 2D surface. The next topic is induced EMF. So for this, I'm going to look at a conducting bar moving perpendicular to a magnetic field. So shown here is a bar moving to the right and a magnetic field into the page. And then since the bar is in motion, the individual negative charges inside the bar, or the electrons, are also moving to the right. And then because electrons are free to move in a conductor, if I use the left-hand rule, the velocity is to the right, so my thumb would be to the right. The field's into the page, so fingers pointing to the page. The magnetic force here would be pointing down. This will cause electrons to have a downward force on them. And then the electrons will move to the bottom of the rod, meaning that the top of the rod is left positively charged while the bottom's negatively charged. So the magnetic force forces the negative charges down. That leaves the top of the bar positively charged, which means that negative charges in the bar also experience an upwards electric force. And the charges are going to flow as long as there's a net force. Once the electric force equals the magnetic force, charges will no longer flow. And that occurs when the electric field magnitude times the charge magnitude, which is the electric force, equals charge times velocity times the magnetic field, which is the magnetic force. Here, Q cancels. And then for electric field, this charge difference means there's a potential difference across the bar. I'm going to call this epsilon. This epsilon here is for something called induced EMF. It's induced because the potential difference came from moving the charge. And what I get from this is the equation induced EMF in a moving bar is equal to the velocity of the bar times the magnetic field that's perpendicular to times the length of the bar. If the bar is placed in a completed circular loop, then the moving bar creates a current due to its induced EMF. So if I say that the bar moves for a time t, it'll sweep out an area of A. Now that area has magnetic field going through it, which means there's a flux, which is the magnetic field magnitude times that area. That area is a rectangle. One of the sides of the rectangle is the length of the bar. The other side is found by Vt, the average velocity of the bar, times the time t it was moving for. So I can replace area with length times Vt. And then in this expression here, I have BLV, which was equal to induced EMF. So from here I can write that phi over t equals the induced EMF, or the rate of change of flux is equal to the induced EMF. And this is a rudimentary statement of Faraday's law. So Faraday's law states that the induced EMF in a conducting loop is equal to the rate of change of magnetic flux over time through the area bounded by a circuit. As an equation, Faraday's law looks like this. So induced EMF equals delta, or change in phi, flux, over delta t, change in time. Flux is BA cosine theta, which means that there's three ways to change flux and induce an EMF. The magnetic field strength can be changed to induce flux You can also change the area of the loop for which the circuit is running through, or the angle can be changed, which is done by spinning a magnet, which is how most electrical power generators work. A way to generate more electrical power is flux linkage, or using many loops of wire instead of one, since there's flux and therefore induced EMF through each loop of wire. And then here, the induced EMF is equal to n, the number of loops, times the rate of change of flux. Now, there's a negative sign out in front of the change in flux, and this is where most students have difficulty when it comes to Faraday's law. The negative sign is a statement of Lenz's law, which states that the induced EMF creates a current that in turn induces a magnetic field to oppose the change in flux. The change in flux thing is where most difficulties will arise. The induced field tries to keep the flux doing what it was doing. It's basically kind of a magnetic inertia. So if flux is trying to increase, then the induced current will act against it. So I'll look at it in more detail. Here the field is to the right, which means the flux through the loop will also be to the right. Now, since the magnet is approaching the loop, the field is getting stronger. So that means the flux is increasing. And then the induced field wants to act against that change in flux. So what I'll do here is I have an induced field trying to push against the change in flux to the left. So I'll point the thumb of my right hand to the left. And by the right hand rule, my fingers would curl counterclockwise. So the current here is counterclockwise. If the flux decreases, then the current is induced to try to prevent it from decreasing. So here I'm trying to keep the flux as it is. So I point my thumb to the right in the direction of flux. Here my fingers would curl in the opposite direction. So as seen from this angle, the current would be clockwise. In short, if flux increases, point the thumb opposite the flux, and if it decreases, point the thumb in the same direction of flux. In each case, your fingers will curl in the direction of the induced current. I have 3 examples here of sort of typical questions with Faraday's law. The first one is a right-hand rule question. So it has a current-carrying wire with current running upwards, and then there's a loop to the right of it, which will have an induced current in it because the current in the wire will increase. So first I want to find the direction of the magnetic field through the loop of wire. I use the right-hand rule for that. If I take my right hand, point my thumb up, my fingers would curl into the page on the right side of the wire where the loop is. And then since the current is increasing, that means the magnetic field through the loop is increasing, which means the flux is increasing. And due to Lenz's law, the induced field created by the current is trying to act against that. So to act against it increasing, I'm going to point my thumb against the field out of the page. And when I point my thumb out of the page, in this case, my fingers are going to curl counterclockwise. So here, the induced current is counterclockwise to create an induced field out of the page to act against the field into the page trying to increase. In part B, the current's now trying to decrease. So the field is still into the page, but it's decreasing, and that means the change of flux is out of the page. So I'm trying to stop the current from decreasing. So to stop something from decreasing, I'm going to try to help it. I'm going to point my thumb into the page to try to keep the inwards field from decreasing. When I point my thumb into the page, here my fingers are going to curl clockwise. So in this case, the induced current is clockwise. The next question involves current being induced by the area through which the field is acting changing. So here I have a rectangular loop. The length is 1.2. That stays the same. But the height of the loop is reduced from 0.6 meters to 0.1 meters. And then it's a loop of wire. There's a resistance of 20. There's a field out of the page of 60 teslas. And then the area is reduced in a time span of 0.2 seconds. And I want to find the induced current. First, I want to figure out whether it's clockwise or counterclockwise. So here the magnetic field is out of the page and it's decreasing. So since the field is out of the page, the flux is out of the page, and I want to stop it from decreasing. To stop the field from decreasing, I would point my thumb out of the page with the field. And in this case, using the right-hand rule, if I point my thumb out of the page, my fingers curl counterclockwise. So the induced current here is counterclockwise. To find the amount of current, first I'll find the voltage or the induced EMF in the loop. So I don't have a negative sign here. The negative sign is already taken care of. Oftentimes in physics, a negative sign refers to direction. So I know the current's counterclockwise. I'm going to leave the negative signs out of the formula now. So induced EMF is delta phi over delta t, rate of change of flux. Now I'm going to write change in flux as field, because that stays constant, times the change in area over time. And then I can just plug in the numbers here. That part's pretty straightforward. And I get that the induced voltage is 180 volts. Ohm's law says that current is voltage over resistance. So if I do that, 180 over 20, I get that the current is 9 amps, and it's counterclockwise. The last example I have here is a situation where a bar is pulled in a magnetic field. And in this case, I want to find the force that this guy is pulling at. So the bar moves at a constant speed of 10 meters per second. The bar is in a loop with a total resistance of 80 ohms due to this light bulb. And then the loop is in a magnetic field of 4 teslas into the page. And the bar the guy is pulling is 3 meters long. So first I'm going to show that the force here is a resistive force acting against the guy pulling the bar. So first I'll find the direction of the induced current in the loop. Here the field is into the page, so the flux is into the page. And the flux is going to be in the area bounded by this loop. As the guy pulls the bar to the left, that area is increasing, so the flux is increasing. So I have a field into the page and increasing. To act against that increasing into the page field, I want to induce a field out of the page with the induced current, so I point my thumb out of the page. By the right-hand rule, my fingers will curl counterclockwise, so my induced current here is counterclockwise. And then because there's an induced current, I have current flowing down through the bar, which means there's a magnetic force on that bar. And then if I use the right-hand rule for the force on a moving bar, I point my thumb down in the direction of current, and my fingers into the page. When I do that, my palm points to the right. So I have a resistive magnetic force to the right. And whenever you have this type of situation where a bar is being moved through a magnetic field, the magnetic force will always act as a resistive force. Now to find the magnitude of that force, since it's moving at constant speed, the net force has to be 0, which means the force the guy is pulling at equals the magnetic force. The force on a bar with a given length and a current going through it is given by magnetic field magnitude, current in the bar times length, or Bill. I know the magnetic field magnitude and length here. The current is the induced EMF over the resistance of the loop. And then earlier, I derived a formula for the induced EMF in a bar moving in a magnetic field. That was BLV. So simplifying, I get B squared L squared V over R. And that expression gives the general formula for the force on a bar being moved through a magnetic field. It's field magnitude squared times length squared times velocity of the bar over resistance of the bar. And when I plug in numbers here, I get that both the force the guy is pulling at and the magnetic force, because they're equal, equals 18 newtons.